4-bit int 8 PTQ. You've seen these terms everywhere. You know they're used to shrink large models, make them faster, more efficient. But the underlying mechanism, the how and the why, for most of us, it remains a total black box. And we're here today to change that. It's time to stop using these powerful techniques as if they're some kind of magic. We're not just going to call a library function and cross our fingers. No, we are going to master the math to truly grasp the engineering principles that make all of this work.
So here's the plan. In the next 30 minutes, we are going to decode that black box into its first principles. Here's what we'll cover. First, the quantization algorithm itself, the fundamental affine transform. Second, we'll break down its core parameters, scale, which we'll call S, and 0 point, which we'll call Z. Third, we'll talk granularity. This is a huge one, the critical trade-off between per tensor versus per channel quantization. Fourth, we'll dive deep into the 4-bit standard and why a concept called group size is absolutely essential to prevent catastrophic quality loss. And finally, we'll cover deployment, looking at the practical difference between PTQ, post-training quantization, and its alternative, QAT. This all comes down to the core mechanism, these two formulas you see on the screen. First, quantization. This is where we go from a float to an integer. It looks a little intimidating, right? And second, dequantization, where we go back from that integer to an approximate float. Right now, these are probably just abstract symbols. They might not mean much, but by the end of our session, I promise you they will not be abstract. You will understand exactly what each component does and why it's there. Let's begin. The fundamental challenge of quantization is actually pretty simple to state. How do we take the world of infinite real numbers, numbers with endless decimal places, and map them down to a tiny, finite set of integers? In our case, just 256 integers. It sounds impossible, right? But it's not. It's just math. So, where do we start? We have to begin with how computers currently store numbers in our models. And that format is called FP32, or floating point 32-bit. Every single number, every weight in your model is stored using this 32-bit structure. It's broken into 3 parts. First, you have a single bit for the sign. Is the number positive or negative? Simple enough. Next, you have an 8-bit exponent. This part determines the magnitude of the number. Is it huge or is it tiny? It controls the range. And finally, you have the mantissa, which gets a whopping 23 bits. This stores the actual digits of the number, its precision. All these pieces get combined using this, well, slightly scary-looking formula you see on the screen. Value equals -1 to the power of s times 1 plus mantissa times 2 to the power of the exponent minus 127. Look, you do not need to memorize this. The key takeaway is that it's a complex system designed for high precision and a massive dynamic range. Let's make that concrete. How would we store a simple number like 3.5? First, the sign is positive, so that sign bit is a 0. Easy. Next, in scientific notation, 3.5 is 1.11 in binary times 2 to the power of 1. That power, 1, is used to calculate our exponent. We add a bias of 127. So 1 plus 127 is 128, which in binary is 1000000. That's our 8-bit exponent. Finally, the part after the decimal in our scientific notation, the .11, becomes our mantissa. We just pad it with a bunch of zeros to fill up the 23 bits. And there you have it. You put all 3 parts together, the sign, the exponent, and the mantissa, and you get the 32-bit representation for the number 3.5. It's a lot of work for one number, isn't it? And that brings us to the core problem. FP32 is greedy. How greedy? Well, think about a 7 billion parameter model. Each of those 7 billion weights takes up 4 bytes of memory. Do the math. And that's 28 gigabytes of VRAM. And that's just for the weights. You haven't even loaded the optimizer or the activations or anything else. This is the bottleneck. This is why you can't run big models on smaller hardware. But what if we could find a simpler way? This is the solution. We map that complex 4-byte FP32 number into a simple 1-byte int8, an 8-bit integer. It's just a number. It can hold any value from -128 to +127. That's it. No sign bit, no exponent, no mantissa, just the number itself. The result? It's 4 times smaller. That 28 gigabyte model, it's now just 7 gigabytes. Now that is a game changer. Okay, so how do we do this mapping? The technique is called affine quantization, and the best way to think about it is this. On the left, you have your continuous float range. Imagine a number line from, say, -3.5 to +3.5. There are infinite possible values on that line. Our goal is to take that infinite line and map every point on it into one of a few discrete integer buckets. In the case of int8, we only have 256 of these buckets, from -128 all the way to +127. We are forcing infinite possibilities into a finite space. To do this, we need 2 key parameters. The first is the scale, which we'll call s. You can think of the scale as the step size. It tells us how much we move in the float world for every one step we take in the integer world. The formula is simple. It's just the float range divided by the integer range. For int8, that integer range is always 255. That's 127 minus -128. The second parameter is the 0 point, which we'll call z. The 0 point is all about alignment. Its job is to make sure that the number 0.0 in the float world maps correctly to an integer. Now, there are 2 main flavors here. For model weights, the range of values is usually centered nicely around 0, like from -3.5 to 3.5. This is called symmetric, and in this case, the 0 point is just 0. It's the standard for weights. But sometimes, for things like activations after a ReLU function, the range is shifted, maybe from 0 to 10. This is asymmetric, and there you'd need a non-zero z to handle the shift. For today, we're focusing on the simple symmetric case. And all of this, all of quantization, boils down to these 2 master formulas. First, to quantize, or encode a float into an int, we take our float, x, divide it by the scale s, add the 0 point z, round it to the nearest whole number, and then clamp it to make sure it's in our allowed range from -128 to 127. That gives us our integer q. Second, to dequantize, or decode the integer back into a float, we do the reverse. We take our integer q, subtract the 0 point z, and multiply by the scale s. That gives us our restored value x hat. It's not the original value, but an approximation of it. Let's see this in action. Imagine we have this small tensor of weights, 1.2, -3.5, 0.8, and so on. Step 1, we have to calculate our scale parameter. First, we find the maximum absolute value in our tensor, which is 3.5. This defines our float range, from -3.5 to +3.5, for a total span of 7.0. Our integer range, as we said, is 255, so we just divide. S equals 7.0 divided by 255, which is approximately 0.02745. That's our scale, our magic number. Okay, step 2. Let's quantize the first value in our tensor, x equals 1.2. We'll use our scale, s, and a 0 point of 0 since we're doing symmetric quantization. Let's follow the formula. First, we divide x by the scale. 1.2 divided by 0.02745 is about 43.715. Second, we round that to the nearest integer. The round of 43.715 is 44. That's it. The float value 1.2 is now represented by the int8 integer 44. Now for the crucial part. Step 3. Let's dequantize it and check the error. We take our quantized integer, 44, and multiply it by the scale. 44 times 0.02745 gives us 1.2078. Look at that. The original was 1.2000. The restored value is 1.2078. The difference, that tiny plus 0.0078, that is the quantization error. It's the price we pay for compression. And of course, you wouldn't do this by hand. Here's what it looks like in Python with NumPy. We'd write a function, let's call it symmetric quantize. Inside, we just follow the steps. 1. Calculate the scale by finding the max absolute value and dividing by 127. 2. Quantize by dividing the whole tensor by the scale and rounding it. And 3. Clamp the results to the valid int8 range of -128 to 127 and set the data type to int8. It's a direct translation of the math into code. So here's the full picture for our example tensor. You can see in this table, for each original float value, like 1.2, we divide by the scale to get 43.71, round it to the integer 44, and when we restore it, we get 1.21, with a tiny error of -0.01. Look at the value 0.8. It maps to the integer 29, and when restored, it's 0.80. The error is basically 0. And even for the most extreme values, like -3.5, it maps to -127, and the restored value is -3.49. The error is still incredibly small. This brings us to the fundamental trade-off of this entire process. What is the cost of all this amazing compression and efficiency? It's this small but unavoidable quantization error. The art and science of advanced quantization is all about managing and minimizing this error, which is exactly what we're going to talk about next. So we've mastered the basic algorithm for compressing numbers. The big question now is, where do we actually apply this inside a real neural network? Well, at its heart, a neural network layer does one simple thing. It performs a matrix multiplication. A layer is just matmul. As you see here, the output equals the input matrix multiplied by the weights. So let's break that down. The two components are the input and the weights. First, the weights. You can think of these as the model's brain. It's all the learned knowledge from weeks of heavy training. These are static. They don't change during inference, and they are huge. For a 7 billion parameter model, this brain is the 28 gigabytes of data we need to shrink. It's the part that lives permanently in your GPU's VRAM. Now what about the inputs? Think of these as the model's thought. This is the user prompt data, the stuff that's actively flowing through the model right now. This data is dynamic. It's new for every single token you generate. And it's transient. It's used for one calculation and then it's discarded. This data lives in the GPU's super-fast cache, but only for a moment. So, looking at this formula again, output equals input at weights. What do we compress? We have a choice to make. Do we compress the weights? Yes, absolutely. Do we compress the inputs? No, we don't. And this comes down to a critical engineering choice. First, why do we quantize the weights? Because they are the memory bottleneck. Compressing that massive 28 gigabyte brain down to 7 gigabytes is our primary goal. This is the whole ballgame. Second, why do we not quantize the inputs or activations? Because they are computationally expensive to deal with. Think about it. If you compress them, you'd have to add a quantize step and a dequantize step at every single layer. That just slows down inference, which is the exact opposite of what we want. This leads us to the industry standard approach, weights-only quantization. But this brings up a new problem. How can you multiply an int8 number with an FP16 number? Isn't that a hardware incompatibility? The answer is a beautiful, elegant solution. It's a trick called on-the-fly dequantization. Let me walk you through exactly how this works, step by step. Step 1 is storage. As you see here, in the main VRAM, our large weights are stored in their compressed int8 format, and right next to them, we store their FP16 scale factor. Meanwhile, the input is just waiting, ready to go in its normal high-precision FP16 format. Step 2, load. The GPU core pulls the compressed int8 weights it needs from VRAM into its own extremely fast on-chip cache. Step 3, dequantize. Now here's the magic. Nanoseconds, literally nanoseconds before the math happens, a specialized circuit on the GPU expands those int8 weights back into temporary FP16 weights. You can see the formula right there. The temporary FP16 weight is just the int8 weight multiplied by its scale, S. It happens in the blink of an eye. And finally, step 4, compute and discard.
The matrix multiplication happens with both inputs now in full FP16 precision. We get our result, and that temporary weight we just created, it's immediately discarded. It's gone. It only existed for a fraction of a second, and the permanent weight in VRAM stays compressed the whole time. This means we get the math accuracy of high precision with zero memory penalty. So what's the verdict? What does this amazing trick get us? A 75% reduction in memory usage with almost 0% loss in accuracy. It's the best of both worlds. But there is a catch. A really, really big one. There is one scenario where this entire system falls apart. One giant value destroys precision. Let's look at the outlier scenario. Imagine we have a list of weights just like before. We have 1.2, negative 3.5, 0.8, all normal values. But then we have one specialist weight, a value of 1,000. The normal range here is around 3.5, but that outlier is orders of magnitude larger. So what happens when we try to quantize this? Let's follow our process. Step 1. Calculate the global scale. We find the max absolute value, which is obviously 1000.0. Now we calculate our scale, S. It's the max absolute value divided by our integer limit, 127. So 1000 divided by 127 gives us a scale of about 7.87. The scale is huge, and that is a big problem. Here's why. Let's go to step 2, quantize a normal value. We'll take our first weight, 1.2. To quantize it, we divide it by that huge scale we just calculated. So 1.2 divided by 7.87 equals 0.152. Then we have to round that to the nearest integer. And what's round of 0.152? It's 0. And here is the disaster. The information loss. Our original value was 1.2, but when we restore it, we take our quantized value, 0, and multiply it by the scale, 7.87. And 0 times anything is 0. The 1.2 was completely erased. The outlier squashed it into nothing. All of our normal, important values are getting destroyed because of one single misbehaving weight. So, what's the solution? How do we fix this catastrophic failure? The solution is a beautiful and simple concept. Granularity. Let's break down the different levels of granularity. First, we have per tensor quantization. This is the baseline method we've been using. You can think of it as one scale to rule them all. We calculate one single scale factor, S, for the entire matrix. The problem, as we just saw, is that one outlier ruins the whole thing. So we get more granular. Method 2 is per channel quantization. This is the int8 standard. Instead of one scale for the whole matrix, we calculate a separate scale for each row or output neuron. Look at the diagram. We have S1 for the first row, S2 for the second, and so on. What's the benefit? The outlier now only hurts row 2. Rows 1, 3, and 4, they remain perfectly precise because they have their own properly sized scales. We've isolated the damage. Let's see this in code. It's actually super simple. We import NumPy as NP, then we create a weight matrix with 3 rows, or channels. You can see channel 1 and 3 look okay, but channel 2, bam! There's our 1000.0 outlier. Now, here's the key. To calculate the scale, we take the max absolute value, but we do it for each row. We set axis equals 1. This tells NumPy to work row by row. This means our result for the scales isn't a single number anymore. It's a list of 3 numbers. And look at the output. The first scale is tiny, 0.022. The third scale is also tiny, 0.024. But the second scale, for the row with the outlier, is 7.87. It's huge, but the corruption is contained. It only affects that one index. But what if we need even more precision? We can go one level deeper. Method 3, group-wise quantization. This is the standard for 4-bit models. Here, we take each row and break it into even smaller blocks, maybe 64 or 128 weights at a time. And each of those little blocks gets its own scale factor. The precision here is maximized because any outlier is isolated to a tiny, tiny group of weights. The trade-off? Well, you have to store a lot more scale factors, which takes up a little more memory. So here's the rule of thumb. This table breaks it down perfectly. Per tensor quantization is the baseline. It has the lowest quality and the lowest overhead. Per channel is the standard for int 8. It gives you good quality for medium overhead. And finally, groupwise is the standard for 4-bit. It gives you the highest quality, but also has the highest overhead for storing all those scales. If you remember one thing from this chapter, let it be this. Granularity controls quality. By isolating outliers into smaller and smaller groups, we preserve the precision of the model, making even aggressive 4-bit quantization possible. We went from 16-bit floats to 8-bit integers. We halved the memory. But what if we could have it again? Let's look at the VRAM math for a 7 billion parameter model. This is where it gets really exciting. As you can see in this table, with FP16, or 16 bits per weight, you need 14 gigabytes of VRAM. That's a lot. With int 8, we cut that in half to 7 gigs, a solid 2x saving. But with int 4, only 4 bits per weight, we get down to just 3.5 gigabytes. That is a 4x reduction in memory. And what does that mean? Now it fits on a laptop. This is the game changer.
But there's a problem. A physical limitation. It's called the byte barrier. Here's the thing. Your computer's hardware, the actual silicon, it reads memory in chunks of 8 bits called a byte. It's physically impossible for it to read just 4 bits. So how on earth do we do this? The solution is actually pretty clever. It's called packing. We take two 4-bit values, for example, the number 10, which is 1010 in binary, and the number 5, which is 0101, and we literally just squeeze them together into a single 8-bit byte. We shift one value to fill the upper half of the byte, and the other fills the lower half. 2 numbers, 1 byte. Problem solved. Okay, so let's talk about the algorithm. The math is similar, but the stakes are much higher. First, we're working with a tiny range. Instead of 256 values, we only have 16 possible integer values to work with, from -8 to +7. That's not a lot of room for error. The scale formula reflects this. It's S equals the max absolute value of x divided by 7. Just 7. That's our new maximum. Because this range is so small, there is a critical requirement. We must use groupwise quantization. Trying to squish an entire tensor into just 16 buckets would be a catastrophe. It would completely destroy the model's accuracy. We have to work in small, isolated groups. Let's walk through step 1, quantizing a group. Here's our example group of weights, 0.51, 0.58, -1.2, and 2.1. Now notice how close those first two values are, 0.51 and 0.58. They're different, distinct numbers. Okay, let's calculate the scale. The maximum absolute value here is 2.1, so our scale S is 2.1 divided by 7, which is 0.3. Now for the tricky part, we apply that scale, and here's where we see the trade-off. Our first value, 0.51, divided by our scale of 0.3 equals 1.7. Round that and we get 2. Now for the second value, 0.58 divided by 0.3 is 1.93. Round that and we also get 2. We have a collision. Two distinct floating point numbers have been crushed into the exact same integer. The distinction is lost. This is the precision we sacrifice for that incredible memory saving. All right, step 2, packing. We have our quantized integers, let's say 2 and -4. The first thing we do is represent them as unsigned integers, so 2 becomes 10 and -4 becomes 4. Now we take our first value, 10, and leave it as is. Then we take our second value, 4, and we perform a bitwise shift, moving it 4 places to the left. This pops it into the upper half of the byte. Then we use a simple OR operation to merge them. And the result is a single packed byte with a decimal value of 74. Here's what that looks like in code, and it's surprisingly simple. We define our numbers, first num equals 10, second num equals 4,
Then the magic line, packed byte equals second num shifted left by 4, or first num. That's it. And the output? Exactly what we predicted. The packed value is 74, which in binary is 01001010. We've successfully stored two numbers in the space of 1. And with that, the memory problem is solved. And the deployment problem has just started. We can now get these incredible models running on devices we never thought possible. Okay, we've gone deep into the mechanics. We've seen how to take massive floating point numbers and shrink them down into tiny integers. We know the how. Now it's time to answer the final critical question. The when. When in the whole process do you actually do this? There are two main strategies. First, we have PTQ, or post-training quantization. I like to call this one the simple path. And then we have QAT, or quantization-aware training. This is the heavy lifter. So which one should you use? Well, let me make this really, really simple for you. PTQ is the standard. Full stop. This is the default choice for almost everyone working with large language models. Let's look at the PTQ workflow to see why it's so popular. It's all about optimizing a model that's already been trained, and it only takes a few minutes. As you can see in this flowchart, you start with your trained FP16 model. The first real step is called calibration. This is the key step. Here, you just run about 100 data samples through the model, not to train it, but just to find the minimum and maximum value ranges of the activations. There's no backpropagation, no training at all. Once you have those ranges, you use them to calculate the best possible scales, and then you move to the quantization step. You convert the weights, and finally, you save your shiny new int8 model. That's it.
So, why does PTQ win?
3 big reasons. First, it is fast and efficient. We're talking minutes on a single GPU, not days. Second, it's great for data privacy. You don't need the original, massive, often proprietary training dataset, just a tiny, representative sample for calibration. And finally, with the modern techniques we've discussed, like group-wise quantization, it is good enough. The accuracy loss is often completely negligible. But what if it's not? What if you run PTQ and the model just breaks? What if the accuracy drop is too much to handle? Enter QAT, Quantization Aware Training. The core mechanism behind QAT is a clever trick called fake quantization that happens during the fine-tuning process. Here's how it works inside the training loop. The model starts with its original FP32 weights, but then it runs a simulation. For a brief moment, it rounds a weight to int8, and then immediately converts it right back to FP32. This process adds a tiny bit of noise or error, creating a slightly damaged version of the weight. And this is the crucial part. The model uses that damaged value for its forward pass. It literally feels the error that quantization will eventually cause. And because it's in a training loop, backpropagation kicks in, and the model updates its weights to become more robust and resistant to that specific kind of error.
So let's look at the trade-offs. As you can see in this table, the choice becomes pretty clear. For complexity, PTQ is low. It's basically plug and play. QAT, on the other hand, is high. You need a full training pipeline. For data needed, PTQ just needs a tiny calibration set, 100 samples. QAT needs the full training dataset. And for compute cost, PTQ takes minutes. QAT can take days of GPU hours. So when would you use them? PTQ is best for basically all modern LLMs, like Llama or GPT. QAT is usually reserved for older computer vision models, or for pushing models onto tiny edge devices, especially if you're going all the way down to int4. This brings us to the final decision matrix. And it's incredibly simple. Start with PTQ. Seriously, it works for 99% of LLM use cases. It's faster, cheaper, and with modern methods, it's just as good. Only if you hit that 1% edge case where performance drops should you even consider QAT as a backup plan. And with that, the final piece of the puzzle falls into place. The black box of quantization has been decoded. We started with jargon. Remember? All those technical terms, int8, 4-bit, PTQ, group size.
They were just a list of confusing words. But now, they are decisions. They're tools you understand, tools you can use. Let's do a final recap of your core knowledge, the absolute fundamentals you have mastered. First, the math. You know it's all built on a simple affine transform. That little formula, Q equals round of x over s plus z. That's the heart of everything. Second, the hardware. You get the trick. It's all about weights-only compression. We store the weights in compact int format, but we do the actual compute in high-precision FP. Best of both worlds. Third, the quality. You know that granularity kills outliers. That's why we isolate them. We use per-channel quantization for int 8 and the even more granular group-wise method for int 4. And finally, number 4, the strategy. You know that PTQ is the industry standard. It is fast, it keeps your data private, and honestly, it's incredibly effective. Let's just look at that one more time. The algorithm is simple. It's just mapping a range, taking those infinite floats and squeezing them down into discrete integers. That's the entire game. And the hardware trick? It's so clever. The compressed int weights sit in your VRAM, saving tons of space and bandwidth. Then, right at the last second, they're zapped over to the GPU core and dequantized back to high-precision FP format. This is how we preserve all that accuracy during the actual computation. And how do we handle those pesky outliers? The ones that can ruin everything. We isolate them to survive. For int 8, we give each channel its own little quantization range. For int 4, we go even smaller, breaking them into tiny groups to contain the damage. Okay, let's put it all together in a reality check. Imagine we have a 7 billion parameter model. Our target is to get this thing to fit on consumer hardware. As you can see in the table, the baseline model in FP16 takes up about 14 gigabytes of VRAM. That's a lot. Most people can't run that. But now, let's apply our knowledge. We use int 8 with per-channel PTQ, and just like that, we're down to 7 gigabytes. We just cut the memory in half. But wait, there's more! We bring out the heavy artillery, int 4 with group-wise PTQ, and boom, 3.5 gigabytes. That will run on almost any modern gaming GPU. This is the point. You don't just know what these techniques are, you understand the why they were designed this way from the hardware up. And because you know the why, you now have the framework, the mental model to understand, evaluate, and implement the methods that power the entire world of efficient deep learning. The black box has been decoded.